Hello, everybody. Here I am. This is our first real lecture. There's my Sunshine Pills logo. Remember, every day is a Bluebird Day. Sunshine Pills. Hey, it cures everything. Anything you can think of is cured by Sunshine Pills. That's why I love them so much. You'll hear a lot more about this as we go. So let's go ahead and get started here. I know I feel like I'm nuts with Sunshine Pills. Maybe I am nuts because I take Sunshine Pills. Hey, like I said, every day's a Bluebird Day. By the way, I didn't mention in the last video that I do have a YouTube channel, and that YouTube channel has a lot of videos that you can use to improve your performance in this course. I do urge you to subscribe. It helps me out so I can continue to produce these great educational videos. In fact, last semester, I gave people extra credit for subscribing. You just have to prove to me that you subscribe to my channel. But it's there and it's available if you like watching videos on statistics or skiing or some other stuff that I do. Good for you. All right, let's get going with this new chapter. Let's talk about the research process all around. So good researchers are always making observations, and these observations result in questions, right? What kind of questions are they? They're questions that we can use to guide our studies. But here's an example. An observation that I often make is that aggressive drivers seem very impatient. They make inappropriate lane changes and tailgate. I see that a lot, especially when I go up to big snow in the American Dream up in the Meadowlands right outside of New York City to go to the indoor ski area. I'm driving home and people are driving like nuts, especially in Jersey, closer to, as we get closer to Pennsylvania on 78, people are nuts. See lane changes, and it even says high accident area. So my research question is, are aggressive drivers less patient than drivers in general? See, that's a really good research question. It came from an observation that I made, but notice how the research question is much more specific, right? It's very, very specific. Are drivers less patient than drivers in general? Even offers a direction, like less patient rather than more patient, right? So it's a directional. Researchers are thinkers, and thinkers propose hypotheses to answer their questions. So we can make hypotheses based on some research question that we formulated. A hypothesis is a falsifiable statement about the relations among variables. Notice it says falsifiable, because people make statements all the time that one cannot falsify, particularly when talking about politics, religion, and issues like that. It's really hard to falsify some of those, but in science, we have to have a question that is falsifiable. We generate our hypotheses from two different types of reasoning. One is deductive reasoning, and the other is inductive reasoning. Inductive reasoning is using observation to inform hypotheses. So it's a bottom-up process. So like the example I said earlier, where I saw people making inappropriate lane changes. So from that, I formulated a hypothesis. Even, after doing a lot of research, you can generate theories from these hypotheses. So that's the inductive reasoning process. Deductive reasoning is a top-down process. We use existing theory to inform hypotheses. Both of these are valid ways of doing research. I mean, that's generally how we start research. Some people just go the deductive mode, and others are more inductive, if you will. I mean, not saying that those are two different types of people, but there definitely are people who tend to focus on reading the literature and trying to come up with different hypotheses based on the theories that they've read. They are more deductive in nature. I like being inductive. I'll use both. So let's talk more about hypotheses and this null hypothesis significance testing. So null hypothesis significance testing starts with a null hypothesis, and we make an assumption that this null hypothesis is true. So what is a null hypothesis? It's a hypothesis a researcher seeks to reject in favor of the alternative hypothesis. The alternative hypothesis is the research hypothesis. In fact, when you read journal articles, you'll never see, well, you rarely ever see a study broken down into a null and an alternative hypothesis. Basically, people just state their research hypothesis, and that's that, right? So there's an assumption, an underlying assumption of the null hypothesis. Let's go to back to the aggressive drivers example. So my hypothesis here is aggressive drivers are less patient than drivers on average. Thus, they drive more aggressively to get to their destinations faster. So I'm making a statement here, making a claim. This is what I'm interested in, if you will, proving, if I could, right? That aggressive drivers are less patient, or they're more impatient than drivers on average. But that's not my null hypothesis. That would be my research hypothesis, right? So that would actually fit under alternative hypothesis. My research hypothesis, my null hypothesis would be that, well, the null hypothesis is the hypothesis we'd like to reject. And generally, the thing we want to reject is that there's no effect, right? So for instance, here, my null hypothesis is aggressive drivers do not differ from non-aggressive drivers on patients, right? So that's what I'd like to reject, because I'm claiming that aggressive drivers are less patient than non-aggressive drivers. So in order to support this claim, I have to reject this claim. That's what we call null hypothesis significance testing. By the way, you'll notice how I listed null and alternative, and I started using symbols here. I used H sub 0, and then I used H sub A for my alternative. So H sub 0 represents my null, and H sub A represents my alternative hypothesis. Some people do H sub 0 and H sub 1. Sometimes they just write them out, null and alternative hypothesis. But either way, using null hypothesis significance testing, the onus is on the researcher to find support for the alternative hypothesis, with the assumption that the null hypothesis is true. So we're always assuming that the null hypothesis is true. So we assume that we failed until evidence shows otherwise. You can contrast this with people who do things like testimonials. They sell products like the nutritional supplement industry. They just make these claims without a burden of proof on them. They put the burden of proof on the consumer. Like, it's up to you to discover whether or not this works. You just have to give me the money. I don't care about anything else, right? So that's what they're working with. We in science go the other way. And this is one reason, by the way, if you're interested in why we have so many problems with people believing in science now, is because we seem a lot more wishy-washy, right? Because we're always starting with, well, we're wrong and we need evidence to support our hypothesis. That sounds really wishy-washy compared to somebody who says, the vaccine does not work. That's what I've been hearing everywhere, right? The vaccine does not work. Or the vaccine, I heard somebody in a line this summer. I was standing in a line to catch a bus we were at this air show. And this guy was like, the vaccine has killed more people than COVID. They make these statements. People make these statements without providing any evidence, right? So in science, we have to provide evidence, because we always assume that we're wrong, right? People like that gentleman did not assume they were wrong. They assumed that they're right. That's not scientific, not scientifical, as like people like to say. So testing hypotheses requires data, right? So I put this under the rubric of inferential statistics. Data are collected from samples of people, right? But we're not interested in the samples. We're more interested in the population as a whole. So we're collecting data so that we can make inferences from the sample to the population. Like if I have a sample of 10 people and I get their blood pressure, and their blood pressure seems to be high, that's telling me something about those people. It may be telling me something about the population, but if I'm working with those individuals, I'm interested in them. But if I'm somebody who's a scientist who's interested in some link between, say, blood pressure and anxiety or something like that, I'm not just interested in those people. I'm interested in all people. So I'd like to be able to make inferences from my sample to the population. That's what we call inferential statistics. Here's an example of what's the average body mass index of the nation's female high school juniors. So we collect data from a sample of female high school students in their junior year. And there's different types of sampling, but what the main type of sampling we like to do is known as random sampling. So you'll learn more about this stuff if you take a research methods course. So I mean, I'll talk about some of it, but but I'll talk about the stuff that we need to know for statistics. So we want to make this inference. To make a good inference, we need a good representation of the population. That's why we use random sampling. So in random sampling, each person has an equal likelihood of being selected into our sample. And it really does a good job of improving ecological validity. Ecological validity occurs when our sample is very representative of the population as a whole. And for that to happen, we need something like random sampling, because random sampling will ensure that we get a good distribution of people. That doesn't guarantee it that we'll have a mix of every person. Like if there's a small cohort of people who are, I don't know, homosexual, female, our random sample may not get any of them or may not get an adequate representation of them. So there's ways we can deal with that with different types of sampling, but that's beyond the scope of this course. Again, in a research methods course, you talk about that. Okay. So we talk about statistics as being inferential in nature because we're trying to make inferences about the population. Discuss variables. We use variables everywhere. Well, variables vary. So something like a person's weight, one person's weight is that person's weight. But if we have 10 people, not everybody's going to have the same weight. There's variability in weight among those 10 people. That's a variable. But variables are functions. They're like, if you ever use a function in math that converts a number into something else, right? But variables are functions that convert elements of a sample space into real numbers. And we need real numbers so we can do math with them. This isn't a qualitative methods course. This is a statistics course, and we deal with quantitative quantities, numbers, quantitative methods. We do math. There are two broad cases of variables. There's discrete variables and there are continuous variables. Under the discrete variables, we have, well, just characteristics of discrete variables. They're finite and countable. Finite meaning that there's a finite number of categories. So something like, for instance, the spectrum of light, there's red, orange, yellow, green, blue, indigo, and violet, right? That's a discrete variable, right? Roy G. Biv. Yeah. Hopefully you know that acronym, mnemonic device for remembering. Sex, we have male and female. Of course, you can call this gender and you can have other genders in there as well. I just use that because I'm old. Smoking status, you have never smoker, experimenter, weekly smoker, daily smoker. These are all example of the finite quality of a discrete variable. Discrete variables can also be countable, like we can count the number of freshmen at LaSalle University, the number of combustible cigarettes smoked in the past 30 days, number of time a person vapes per day, number of alcoholic beverages one drinks per week, etc. By contrast, we have continuous variables, or in contrast, we have continuous variables. Examples of continuous variables are weight, height, and speed. They are non-countable and infinite. So we'll see what we mean by non-countable, but essentially you can divide the difference between any two weights or any two values into an infinite number of divisions, infinite number of segments, right? So you can keep them going down to infinity, get smaller and smaller units there. Therefore, the probability of a specific value on a continuum is zero, because I can divide it into some really, really small amount. Like let's say the difference between 130 and 140 pounds, 10 pounds, but I can also divide that into quarter pounds, ounces, whatever, going down and downing to these really, really small units, so that the probability of any one unit would be zero. That's because you'd basically not find anybody with that specific value. Versus in something like a discrete variable, I'll find a certain number of males and I'll find a certain number of females. These are discrete categories that have mass, right? They have mass. So we actually call the function for this type of variable probability mass function, whereas we call the function for a continuous variable the probability density function. We'll talk more about that later, but remember that the probability of a specific value on a continuum is 0 for a continuous variable. What is a sample space? I'd mentioned sample space. Those are all possible values of a variable. So this is before we translate the variable into numbers. I mean, variables belong there. They belong to these sample spaces, and within those sample spaces, we have these different values, right? So like I could do a random experiment, pick a person out of the blue, and it can be either male or female. Assuming there's only those two categories, it can either be male or female, right? These are two levels of this variable. These are the two elements of this sample space, right? The sample space has only two elements in it, right? But we'd like to be able to convert that into a number so we can use it. Class standing, you have 1, 2, 3, 4 different elements. You got freshman, sophomore, junior, and senior. And again, if I took a person, if I take a person and I want to know what they're like, if any of you, I want to take one of you out and say, what's your class standing, freshman, sophomore, junior, or senior? It's a random experiment, right? That's an experiment. And the outcome of the experiment would either be freshman, sophomore, junior, and senior, because those are the elements of that sample space. Days of the week, I could divide it into, I mean, it could be all 7 days, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday, and Sunday. Or we could have days of the week and weekend days. We could divide the sample space however we want to, right? Social media use, something like Facebook, Twitter, Instagram, other, those are all examples of sample spaces. So you want to be able to convert these elements into numbers using a function. So what would the function look like here? It could be anything. This is where you need to pay attention. So let's say my function, so it's this notation f of x, that's something you'd see in math, right? And x is the element, you enter it like, so I say let x equal Facebook. So f of Facebook would equal what? Well, I can give it any value I want, right? I can say its value is 1. So f of Facebook equals 1. F of Twitter could equal 2. F of Instagram 3. And f of other equals 4. So that's my function. What I'm doing there, I'm taking those values and I'm converting them. So if I were to ask you, can you tell me what the function is for social media use? You would tell me exactly what I just told you there, right? You're assigning a specific value to each of these, and you have to tell me what those values are. So for weekdays and weekend, I could say weekdays is 0, weekend days is 1. So there's my function, right? Converting this sample space into a number. Now we can do math with it. Let's talk more about these types of variables. Under the rubric discrete variable, I'd mentioned discrete variables already once, talking about them being finite and countable. We can also divide them into ordinal variables, nominal variables, ordinal variables, and counts. So nominal variable, well, I just showed you some nominal variables like sex and days of the week. There's no reasoning behind the choice of numbers representing each level. There's absolutely none. So I could say sex, male is 0, female is 1, or female is 0 and male is 1, or female is 1 and male is 2, whatever I want. I can even say female is -1 and male is 36. I could put anything. There's no specific reasoning to that. Clearly, you want to be a little bit more cautious than that. I usually like to create variables that have 2 levels. We call them binary variables, like this one. In this example, where it's male and female only. 0 and 1. One level will be 0 and the other will be 1 for mathematical reasons, because when I multiply by 0, I get 0. And when I multiply by 1, I'll get whatever the value is. So now I can see a true change from between the two different levels of that variable. If there's more, more than 2 levels, you can do whatever you want. By the way, when there's a variable that has 2 levels and I code it, that's what we do when we when we use the function. I coded 0 and 1. That's called a dummy variable. So you'll hear me use that again, I think, at some point. Ordinal variables have a natural ordering to them, like class standing, like freshman is below sophomore, which is below junior, right, and which is below senior. So you have this natural ordering, how you finish in a race, first, second, third, or fourth. Interesting thing about these variables is that the distance between any two contiguous categories is not equal. So for instance, the distance, while you may think the distance between freshman and sophomore is a year, right? That's not necessarily true. It could differ in terms of number of credits required to go from one to the other, but it also differs qualitatively in that, what going from a freshman to a sophomore is qualitatively different from going from a sophomore to a junior. So there's really no consistency in the difference. And of course, counts are when we're just counting something, and we'll be using that when we deal with Poisson random variables. It's when we count things like how many cars pass in a corner in an hour, how many customers are in a store, like in our food pantry, how many people come through the pantry every hour. That's something you'd use a count variable. Those are all discrete variables, and their functions are known as probability mass functions. Continuous variables, the distance between consecutive levels is equal, like the distance between 3 and 4 pounds is equal to the distance between 4 and 5 pounds, right? It's a pound, that doesn't change. And sometimes people like to use interval and ratio as descriptors for continuous variables. Hey, and I may do it too, right? Sometimes people use quantitative variables. So continuous variables can be called quantitative, interval, and ratio variables as well. So you'll see all of those. Intervals, because we have equal intervals, right? Distance between the two values is equal, regardless of where we are, whether it's 10 and 20 pounds or 75 and 85 pounds. The distance is the same. The ratio part is when we have an absolute zero, we can use ratios. Like, for instance, the 0 weight exists, right? Somebody doesn't exist, so they have 0 weight. 10, therefore, since there's an absolute zero, 20 pounds is twice 10 pounds. Where there is no absolute zero, we cannot use ratios. An example would be temperature. While you may think that 50 degrees is twice 25 degrees, yes, the number it is, but 50 degrees isn't twice as hot as 25 degrees. So it's all relative to whatever you're feeling that day. But there's no absolute zero. However, with Kelvin temperature, there is an absolute zero. All right, so any questions about that? By the way, this is my math friend here. Check him out. That's cool. I got lucky to get, they look plushies. It's a pie. Yes, even math numbers have feelings. All right, let's talk about symbols. We use symbols everywhere. Sample statistics use Latin letters. So these are the letters we're using here. You'll see that in a moment. To represent population parameters. Population parameters use Greek letters. So we'll see a lot of Greek letters. Greek letters are also used for mathematical operators. I'm the king of footnotes. I got this footnote thing. So here's a fun fact for you. Fun fact, there are 24 Greek letters, right? Fraternities and sororities use 2 or 3 uppercase Greek letters. The number of possible, so if you're in a fraternity, you're making a fraternity or sorority and you want to give it a name, well, you have a lot of choices here. The number of possible fraternity sorority names is, well, we have, for the first letter, if we're using a 2-letter name, you have 24 choices for the first and 24 choices for the second, right? So that's a product. Because by the way, when we get to probability, whenever I say and, that all means multiplication, right? And for the 3 case, you have 24 for the first and 24 for the second and 24 for the third, right? Well, you have 2 or 3 letter names. By the way, or in probability language is plus. So if we add those up, we get 14,400 possible names. Yikes. A lot of possible names. We should name our ski club like a fraternity. Yeah. I think of some, or sorority, think of some fun names. Here's some common symbols you'll see. So these are Latin letters. So this is representing a sample mean. You have like an X with a bar over it. You can have a Y with a bar. You can have any letter with a bar over it to represent a mean. Sample variance, we have S for, we usually say S for variance. S squared. We'll learn more about this stuff later, so don't worry about it now. Population mean, because we're dealing with a population, it's a Greek letter, it's mu, and population variance is sigma squared. So Greek letters go with population values, Latin letters go with sample values. So here's an example something that I use often, like a focus example. So I make an observation. So here I'll show you the use of the symbols here. Observation is that students focus better when studying in the library than when studying in their dorm rooms. So my null hypothesis, again, I have h sub 0. Notice though that I'm using a Greek letter. So in this case, this Greek letter mu represents the mean. So the mean, I don't know, they study better, whatever. Let's invent some kind of focus measure, right? So the mean level of focus in the library is equal to the mean level of focus in the dorm room. So that's, like I said, null hypothesis. That's what we'd like to nullify. But our observation is that students focus better in the library. So my alternative hypothesis would be something like the mean library focus is greater than the mean dorm focus. Or I could alternatively say the mean library focus is not equal to the mean dorm focus. So these are two possible alternative hypotheses. We'll learn about these differences later. But I just wanted you to see the use of the Greek letters here, because again, we're making inferences from a sample to the population. We're not really interested in a sample, we're interested in the population, what's going on there. Let's talk about summary statistics. Summary statistics are what we use. We also can call these descriptive statistics, but we generally need to summarize our sample in order to provide information to other researchers who are interested in replicating what we found. Science requires replication, right? One finding alone isn't good enough. You have to have the same finding over and over again for it to be meaningful. All right, let's look at some summary statistics. We generally, there's more than this, but we talk about location and spread. If you're interested in like more higher advanced math, these are called moments, right? This is the location is the first moment, the spread is the second moment. We even have a moment generating function. Then we have third and fourth moments. I think it's skewness and kurtosis. These are third and fourth, and so on. Location is the center of the distribution. Spread is a measure of data dispersion. In other words, not everyone has the same value. Common measures of location are the mean and the mode. The mode and the median. Mode and the median. The mode is the most frequently occurring value in an array of values. Like if we're looking at class standing, maybe we have more freshmen than anybody else. That would be the mode, would be freshman. Or if we have more sophomores, the mode would be sophomore, right? So the mode is the most free. So this type of measure of central tendency is probably best for when we're dealing with discrete values, although it can be used with any value, doesn't matter. Any type of variable, excuse me. Median is the middle value in an array of numbers arranged from smallest to largest, or you could do from largest to smallest, but let's just make it smallest to largest to make it simple. How do we find the median? Well, we always take the values and arrange them from low. We'll just go from lowest to highest. If necessary, but it's not always necessary, you'd use this equation to locate the median. This is not going to give you the answer for the median. And in exams, people give me this as the answer. It's obviously wrong. It's the location. N, where n is the number of elements. So if we have 5 elements, n is equal to 5. N plus 1 divided by 2. That'll give us the location. So here's a question. What's the median of the following numbers? 1, 12, 8, 6, 3, and 9. So we arrange them from smallest to largest. We have 1, 3, 6, 8, 9, and 12. That's going from smallest to largest. The location for the median is, well, we have how many numbers? We have 1, 2, 3, 4, 5, 6. So n is equal to 6 because n is equals the number of values. 6 plus 1 is 7, divided by 2 is equal to 3.5. So we can find our median between, well, it's at 3.5, so it's between the values of 3 and 4. So we've got 1, 2, 3, 4. So it's between 6 and 8. That's where our median is located. Okay, so to find the median, when we have an even set of numbers like we do here, we take the average of the two surrounding values. So our two surrounding values here are 8, 6, and 8, right? Because we had to go move 3.5 spaces, like 1, 2, 3. 6 is 3, and 8 is 4. So it's between those two. So we add those two together. 8 and 6 is 14. and divide by 2, and we get 7. And that, my friends, is our median. Of course, in the case where we have an odd number of values, we don't need to do any of that because it's just the middle value. I mean, you can still use the equation to find the median, right? If you have a large array of numbers, but it's basically the number in the middle. So those are location values. With spread, I didn't talk about the mean yet. I'll talk about the mean in a second. For spread, we have different measures. One of them is the range. The range is a terrible measure of spread for a very specific reason, but I'll show you in a second. The spread is the largest value minus the smallest value. So largest value is 12, minus 1, we get 11. It's a terrible measure because what if somebody did a typo or something like that, and instead of 12, they put 112. So now our range is 112 minus 1, 111. Or what if there's somebody who has a very large value for whatever reason, like they have 55. So my range is 55 minus 1, 54. So the range is heavily influenced by what we call outliers or unique cases or extreme cases. So you have to be careful for that. And that's the answer to this question. Sometimes we use the interquartile range or the middle 50% of the distribution. So that's a kind of a cool measure of dispersion because it gets rid of those extreme values. What are quartiles? A quartile is a type of quantile. Quantiles break a distribution into equal parts. Different quantiles are deciles, quintiles, and quartiles. So those are different kind of quantiles. So quantile just break a distribution into equal parts. It doesn't tell us how many equal parts. We have to look at the actual definition or the type of quantile. So quartiles, think about a quarter. Quarter breaks a dollar down, is a quarter is a fourth of a dollar, 4/4 is a dollar. So we break a dollar into 4 equal parts. Let's find the interquartile range for 1, 6, 8, 9, and 12. So let's go through this process. Okay, I mean, we can divide, if we like, into quartiles, right? First quartile is the lowest 25%. The second quartile is the next highest 25%. The third quartile is the next highest 25%. And the fourth quartile is the highest 25%. So the distance between these two endpoints, or these two added together, or these two proportions added together, gives us the interquartile range. So here's the steps for an even number of entries. First, you divide the sample in half. So if we divide the sample in half, we get 1, 3, 6, and 8, 9, 12. Second, we find the median of each half. And finding the median here is easy because it is the middle value. We have an odd number of values. So for the lower half, it's 3, and for the upper half, it's 9. Finally, subtract the lower from the upper half, and we get 9 minus 3 is 6. So our interquartile range is 6. Don't you wish it would be like this throughout the whole semester? That would be awesome. If there's an odd number of values, the middle value is the median. When we divide the sample into two halves, you'd exclude the median and then just follow the same process here. So you just exclude that value and do exactly what you did here. Now, in some textbooks, the authors will tell you to include that value in both the lower and the upper half. Either way is fine. Just always tell people what you're doing. But for us, for our purposes, we're going to exclude, okay? Exclude the median and then follow the same process above. Working with continuous variables is a little bit different because of the nature, because how infinitely divisible a continuous variable is. There's just a lot more there. The best measure of central tendency, and this is going to be assuming the data look like a bell-shaped curve. They're normally distributed. That'll help a lot. Is the mean. The mean is a weighted average. You've probably calculated the average all the time, like what's the average money I get per paycheck or something like that, or the average number of I don't know, if somebody plays sports, the number of hits they get in baseball or something like that. Those are all, or one's rebounding average or points per game in basketball or something like that. Those are all examples of averages. So you probably do these a lot. All you do is add together all the values and divide by the total number of values. Let's go through this equation just to get used to the symbols. First, we're calculating the mean of a sample. So we have the x with a bar. If you recall, the bar above the Latin letter represents a mean. This is a quotient, right? There's a numerator and denominator. In the numerator, we're using a Greek letter, sigma. See that little squiggly thingy? That's a sigma. You should make a sigma plushie to go along with the pi plushie. That'd be cool. This is telling you to add together all of the values of some variable that we call x. It could be weight, height, whatever x is, happiness score. Notice that there's an I here, so it's x sub I. This I stands for individual. So we're adding together all individual values. So if there's 10 individuals, I can be 1, 2, 3, all the way to 10, right? Each individual will have her own score on whatever the variable is. So we add those together, starting with I equals 1. So that's the first person, and going all the way to the nth person. And in this case, I said n was 10 because there's 10 people. So we just add, this is just telling us to take those 10 values and add them together, right? For each individual. You divide it by the number of individuals. If there's 10, it's 10, and voila, you get your mean. The sample mean is an unbiased estimate of the population mean. Boy, that's a cool statement. So it's a good estimate of the population mean. Unbiased, well, you'd have to work that out mathematically. And in fact, I show you how to do it. If you're interested, I show you the proof of sample mean being an unbiased estimate of the population mean. But you can think of it like when you calculate the sample means some of them will be above the population, some will be below the population, and they'll, so that it's unbiased. You're not going to get them in one direction alone. The variance. The equation for the variance is interesting because it shows variability around the mean. And again, we have the sigma for adding together. Now we're adding together some squared values. So this is called a sum of squares, right? You're summing, you're adding something that's squared. Notice here that I suppress the I equals 1 to n because that's a lot of work to put that in there, and I don't feel like it. So from this point forward, it's from 1 to n. And we're saying for each value, each individual's value, we're going to subtract the mean from it. So we want to know what's the dispersion around the mean. A good question would be, why would we square it? If you know that, that's awesome. So we square it because if we didn't, this would probably equal 0, right? Because there's these values, the mean is right in the middle of this distribution, so some values will be above and some will be below, right? So if we don't square it, we're going to get a 0 value, and we don't want to say we have 0 variance. So in order to get rid of the negative values, we square it. And then we divide by n minus 1. If you want to know why we divide by n minus 1, watch another video of mine on my channel. It says the sample variance is an unbiased estimate of the population variance. You'll also see why we divide by n minus 1 if you're looking at that. So this is your regular variance equation. This is actually a shortcut variance equation. Looking at me, you probably think, what the heck is he talking about? That does not look like a shortcut variance equation. It looks more complicated, but it is actually, if you're using something like Excel and you're setting things up, this is so much easier to work with. And by the way, you can use Excel in this course for solving problems. I have no problem with you doing that. I prefer that you learn how to use technology to do work, because in your jobs, whatever you do, if you ever have to do anything with numbers, you better be quick, and you don't want to be doing things by hand. So this is the shortcut formula. It says we're going to sum all the x squares. So we take all these values, we're going to square them. We're going to sum all the x's, square that sum, and divide by n, and then divide this whole thing by n minus 1. You could derive this equation from that equation. I don't know if I show you the simple. Now, I don't show it here, but I do have a video showing you how to derive it. The standard deviation, we'll talk more about what that is when we get into distributions. but the standard deviation is the square root of the variance. So if I ask you for the standard deviation, if you have the variance, you just take its square root and you're done. The mean and standard deviation are best for continuous variables. I think I mentioned that already. It's with this bell-shaped curve. This is beautiful. This is actually a standard normal distribution. We'll learn more about this later. By the way, if we have a perfectly normal distribution, it's perfectly symmetrical, the mean, median, and mode are all equal. Got it? Good. Here's an example from the textbook. Now, you also have problems you can work on in the textbook, so and answers, so you should practice. But here's a problem from the textbook itself. And I gave you these values here. Column is like an ID value, the exam score, and we want to know what the mean, and we want to calculate the mean, variance, and standard deviation of exam scores, right? And we want to use a shortcut formula, right? So what I'm going to show you is how I did this in Excel. Move this sucker. You can't see this stupid thing, but I can keep on moving this little toolbar everywhere. So here it's all done, and here it's not done, right? Or I did do it. Okay, so let's see. So let's start from scratch. Everything from scratch. You can learn how I do all this stuff. All right, here we go. Get rid of everything. I'm getting rid of everything. All right. So, well, according to that let's actually bring the equation over here too. Equation, would you be willing to come over here? Oh, not that equation. I want this one. Control V. Control V. Come on. I hope it works. Here it is. Oh, come on. Enlarge this. There you go. Okay, so there's our equation. So according to this, we need to sum x squared. So we need to square x. So let x equal exam scores. So we use variable name letters, right? Latin letters to represent what we're measuring. So we're going to let x represent exam score. So x can be 22, 42, etc. So we need to square these values, right? These x values. So it says I have a column I set up here called exam score squared. All right, so I'm going to square these. There's different ways to do that. A simple way is to hit the equal sign in the cell in which you want to work. Highlight the value you want to square. Look how this little train looking thingy goes around the cell. And I do this little upside down V. I know there's a name for it, and some of you might know. I don't know what it's called. Caret or something like that. Right? And then I hit this 2, because squaring is multiplying something by itself, power of 2, and I hit enter, and I get 22 squared is 484. Then see this little tiny little green box right here? Look what happens to my cross when I go away. It looks like the Swiss cross. When I get closer, it looks like just a plus sign. Grab that and drag all the way down for all the 10 different values, and it'll calculate it for all of them. So it's squared, 42 squared is 1764, 20 squared is 400, right? Sweet. All right, that's the first thing I know. I need. Second thing is I need the sum of the x's, and then I'm going to square that. So I need to sum the x's. So I have, conveniently, I have a sum here, and I highlight the cell that I want the sum to appear in. Oh, no, these things are always in my way. All right. If I go to the top of my Excel document, I have this sigma, and as you recall, I mentioned sigma means sum. So I hit, I want to do auto sum, so I'm going to do that. Yes, sum. All right. So it's telling me right now it's going to sum cell C3. Notice how it says C3 here to C12. and this is C12 is my 37, and that's what I want. So I hit enter. I can also work up in this little box right here too, just in case. I hit enter, and I got my sum is 330, right? So let's start plugging these in here. So I got 330. Oh, I need to square it, right? I need to square it. So how are we going to square this bad boy? Well, we'll just do what we did. Oh, I could just, I can actually drag this down because remember here I had each cell value in C squared, and I went all the way down to C to this one right here, which is C12 squared, was 1369. If I drag this down one more, it'll square the 330 and I get, right? Get 108,900. 108,900. All right. All right, let's look at what I did before here. Oh, here it is. Why does it say 363? Did I do that right? Let me just make sure everything's okay here. I got 363. Did I get 363? Uh-huh. No, it says 330. Why does it say 330? C3 to C12. Yes, that's 330. Okay, and this is C3. That's right. All right. Well, let's maybe I did something wrong myself. Let's put that in there. 108,900. 108,900. All right. Oh, never mind. I see what I did wrong. No, no, okay. I see what I did wrong. No, that's right. Okay, 108,900. Okay. All right, so we need the x squares too. Let's need the x squares too. Oh, wait, I know what I did wrong. Oh, geez. I apologize. You got to get used to me doing this. I make little errors like this, okay? This is the wrong example. I agree. No wonder it's a little different here. Okay. Okay, so I was doing the wrong problem here. I apologize for that. But let's actually finish that one. So this problem that I was working on is actually here. I was working on the wrong problem. It's this one down here. All right. So let's write some of these values in here. Okay. All right. So that's good. So 42 and 37. Yes. Okay. All right. So sum is 330. That's fun. Sum is 330. I'll help you out here. Sum is 330. All right. Perfect. And then let's see. We had exam score squared. We already did that, right? Exam score squared. Let's do that. Take all these values and move them. Move them over here. See, that's why I like teaching, because when you make errors, you can do something good with them. All right, let's move them here. Here. And all right, cool. So right now we're good. All right. So all right, we got. So let's work with this. All right. Have a little fun here. Have a little fun with me. I'm going to copy this whole thing. Copy and we're going to paste it right here. Control V. All right. And we're going to get rid of everything here, 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 and here. All right. And all right, there you go. All right, so let's do this. All right, so we have sum of the x squared, sum of the x squared. So what was the sum of the x we had? The sum of the x here was 330, right? 330, oops. 330, and we squared 330, right? And I put the wrong value here, and I squared 330. Okay, we got 108,900, right? So we took the 330 and we squared it, and we got 108,900. Okay, and we got 108,900. 108,900. 108,900. There you go. Now we're back to normal. All right, let's make sure how many values we have here. We have 10 individuals, so our n still equals 10. All right, so this still holds 10, 10, right? Good. 10 minus 1 is 9, so this still holds. All right. Next thing we need is the sum of the x squares. So what's the sum of the x squares here? So we have, so now we need to, so this was 330 squared, right? But now we need, so I'm going to delete that, okay? Because that's not what I really need. I just use that as a means to an end. We need to sum these x squared values here, right? So let's go back to Excel. Get rid of this. Now we're going to sum the x squared value. So again, we're going to go to our auto sum. And hit enter. So notice how it highlighted from 484 all the way to 1369, and we hit enter, and we get 11512. So that's the sum of the x squares. It's 11512. So let's plug it in. Sum of the x squares. 11512. All right. So now we could put this in here too. 11512. So what I'm doing here is I'm just translating this equation. But sum of the x squares is 11512. Sum of the x squared, sum of the x was 330. We squared that, we get 108,900. And is 10, right? So now we are left with, and of course, in the denominator, we had 10 minus 1 is 9, right? So we have 9. So now the last thing we have to do is 11512. Oops. 11512 in the numerator minus, well, 108,900 divided by 10 is just, well, just move, when you divide by 10, you move the decimal space one space to the left, because there's only 1 0. So it's 10890 divided by 9. All right, so let's just do this last little bit here. We get 11512 minus 10890, enter, divided by 9, and it gives us 69.111. So 69.111. All right, there you go. Now, in an exam, you just have to show me, you fill in the correct numbers. How you arrive at those numbers, you can use Excel, and I'll show you how I do that here. All right. So let's go back to this here. So I showed you where the 330 came from. That was the sum of all the x values, right? Because it's sum of all the x's, and we squared that. And so if you want, you can do the squaring like this too. You can hit the equal sign again, highlight the value you want to square, use that, I believe it's called a caret, I'm not really sure, whatever it's called. Upwards arrow, 2 for squaring, power of 2, and hit enter, we get 108,900. So that's how I got that value. I squared all these individual values, right? And then I summed them and I got 11512, right? So, and then I just plugged everything into the equation. Very simple in that sense, right? I can check my work. Now, this is not going to be sufficient. Okay, let me just make it clear. This is not going to be sufficient. You have to show me the work. Like, show me where you plug things in. Even when you do the mean, you have to show me how you arrive at the mean. If you recall, the mean is the sum of all the values divided by n. So we had a sum was 330. So 330 divided by 10 would be 33, right? That would be my mean value because I have 10 values. I summed all of them and I got 330 and I've divided it by 10 and I got 33. Now I can also calculate the mean. Now this is where you got to watch me very carefully. There's these internal functions that you can use. Like for instance here, click the function. Let's go to all because like let's assume that we didn't ever use anything, right? And I want to do the mean. The mean is the average, and the average should fall under statistics. So I go to statistical. Sometimes you get math and trig, and we're going to use those too. If I go under statistical and hit, I do statistical, I'll get all the things I need. So we want the average, right? Average returns the average arithmetic mean of its arguments, which can be numbers and names, arrays, references. That's what we want. We want the average. Okay. So hit OK. And it'll give me this box here. It says it's going to give me the average from G14 to H14. Well, that's not what I want, right? Because I want from C2 to C12. So here's what I'm going to do. This is real important to watch. I'm just going to highlight these. And there you go. It changed it. And it actually calculates the mean. It shows me it's 33, but I can hit the number and it's 33. So we got the mean. That's how you're going to check your work. Okay, remember, you're going to complete the work by showing me where the number goes in the equation, right? And if you recall, the equation for the mean was somewhere here, right? Yeah, here. This is from a different problem, okay? All right, now, but that's how you're going to show me. So if you look at the way I did it, was I put the numbers in and then derive the value. Again, this is from a different problem. It's not from the one we're working on right now. So how do I get the variance? So as you can imagine, I can get the variance just as easily. Let's do that. So how do I find the variance? So we want the variance. Function. Well, it's also going to be under statistics. So we look for V for variance. Variance for the sample, because it's divided by n minus 1. For the population, it would be divided by n. So we need the variance for the sample. Hit OK. And right now it's set to be I14 and I15, which is not correct because I need the variance for the same values, right? Again, I'm going to highlight the values of interest, these 10. And I'm going to hit OK, and I see it's 69.111. That's what we calculated. So now I can check my work and say, well, I did a good job. Cool. Last thing we need is the standard deviation. The standard deviation is the square root of the variance. I can do this two different ways. I'm going to show you both. First one is the way you got to show me the work, right? If you recall, with the variance, it was just the square, I mean, the standard deviation was a square root of the variance. So I actually drew this radical sign. I did s squared, and I put the value in here. So you got to do that, okay? Let's get this value. So we have our variance as 69.111. So a standard deviation. I'm going to go to function here. Square root is a math and trig. It's not a statistics function. So I have to go to math and trig. I'm going to go to square root. So it's s, right? Square root. Here it is. Returns the square root of a number. Hit OK. And what's the number I want? So I want the square. So it just wants the cell it's in. It's in this cell right here. Hit OK, and I get 8.313. You shouldn't have to check your work here, but if you are interested in checking your work, you can do the same thing as we did before. You can go to, now this would be going back to statistics. If you want the standard deviation, go back to statistics, go to standard deviation, standard deviation for the sample, not for the population. Hit OK, and it should give us the same value. Highlight all the ones that you need to use. And look, 8.313, right? There you go. Same. So you check your work. Pretty good, huh? Pretty easy. That's what you have to be able to do. One last thing I want to do before we butt out of here. And you can work the other one on your own. I gave you the answer to it, but you can work it, the one that I messed up on. You can work on that one on your own. One thing I wanted to show you here is why we square the numerator in this original function, not this function, but in the original function, right? Why did we square the numerator here? Where's the original function? Here it is. Why do we square the numerator? Well, let's take a look. So if we take each value minus the mean, first thing I need the mean. The mean is 33, right? So I'll take each value. So I have equals this value minus 33. Now I have to put 33 in here. I can't put the cell down here. Unfortunately, if I did that, it would change. It would keep on going down to the different cell. So I have to put a constant in here. So I get minus 11, right? So the next one, I can drag this down here and it'll do 42 minus 33. Look, 42 minus 33, and so on throughout all of these, right? Let's sum these and see what happens. All this stuff always makes me nervous because what if my whole life is a lie, man? Oh, you got to get used to my sense of humor. Sorry. So we're going to sum these bad boys up. And what do we get? 0. I was right. See, we got 0 because you have equal number of basically positives and negatives, right? Surrounding the equal distance to the mean. That's how we get the mean. So the reason we square this is because we know we don't have 0 variability. Remember that for the exam. Well, I'd like to thank you all for a wonderful time today, and I look forward to our next week's presentations. Have a great day.